And the idea behind it is to save us time, I guess, in those probability questions. You remember the basic idea of probability is the number of times an event happens over the total of number of things in the sample space. And sometimes you draw up tree diagrams, dot diagrams, things like that. But look, you don't really want to waste time writing out the whole sample space when all you're interested in is just a couple of the events. And so this topic really is on how we got quicker ways of counting how many times things happen without having to draw all the tree diagrams and things like that. So we start with what's called the basic counting principle, so the basic idea behind this. It's a very, very simple idea, hence probably why it's called the basic counting principle. So if you've got an event and it can happen in m different ways, and then after that you have another event and that can occur in n different ways, then the number of ways the two events can happen would be m times n. Now if we reflect back to a tree diagram, that makes sense because it would branch off. The first event happens, say, 3 ways, so you'd branch off 3. The next event would happen 2 ways, so each of those branches branch off 2. You end up with 3 times 2, 6 branches. So that's the idea. 3 dice are rolled. Okay, so we're assuming normal 6-sided dice here. And so typical sort of question, how many ways can those 3 dice fall? Well, the first dice, it's got 6 possibilities. The second event, which is the second dice, it also has 6 possibilities, and the third one has 6. So all up, 6 times 6 times 6. 6 cubed, which is 216. Okay, but hang on a sec. We want to know that all 3 show the same number. So how many ways can this happen? So we say, well, it's 6 times 1 times 1. And where does that come from? We say, well, whether I throw all 3 at the same time or I throw them one at a time really doesn't matter. So I'll throw the first one. There's 6 different things that could happen. But now I want all 3 to show the same thing. So when I roll the second one, there's now only one thing that could happen. I want it to be the same as that first one. And the third one, same deal. Only has one possibility. Now, that's the idea behind it, using the basic counting principle. Sometimes just pure logic can tell you the answer, because if you think about it, all 3 show the same. Well, they could either be all 1s or all 2s or all 3. There's 6 different things they could be. Which then leads us to the obvious probability question that comes from that. Oh, what's the probability? I'm going to roll 3 dice and they show the same number. Well, it's then that idea, number of ways it can happen over total number of different possibilities. So 6 on 216, 1 on 36. So we're able to get the answer without having to draw up a huge sample space and physically count them all individually. Here's one that uses the same sort of idea from an HSC, well, a fair while ago now. What's that, 22 years ago? Goodness me. So we've got mice, and we're placing these mice in the centre of a maze, and the maze has got 5 exits. And every mouse is equally likely to leave the maze through any of the exits. Okay. So in other words, the probability of a mouse using any of the exits is 1 in 5. Okay, so everything's equally likely. So 4 mice, which we've conveniently labelled A, B, C and D. Maybe we painted it on their backs or something. They're put into the maze, and these mice behave independently. So the first question is, what's the probability that they all come out the same exit? So using this same idea, but doing it with probability, so working out both at the same time, I'm going, well, hang on, that's 1 times a fifth times a fifth times a fifth. What's my logic? Again, it doesn't matter if they all 4 leave at once or they leave 1 at a time. I can think of it as 1 at a time. The first mouse can go through any door. So it's like saying, what's the probability that they leave? Well, I might have to wait a long time, but eventually they'll leave. So probability of 1, it's going to happen. It's a certain event they'll leave the maze unless, I don't know, they have a heart attack thinking about which door will I go through? Squeak, squeak. And then just lies in there. But that's probably unlikely. But there's a probability. But then the next mouse comes along and we want them to go through the same door. So there's a 1 in 5 chance that the second mouse picks it, 1 in 5 chance the third one, and so on, giving us a total probability of 1 in 125 that they all go through the same door. All right. Now the next part of that question. So what's the probability that A, B and C come out the same exit, but D goes out some other exit? Okay. So A, B, C use the same one, D uses a different one. So the way I thought of it was, well, let's look after D. D's just going to go through a door. So there's one chance of it happening. But now that D's gone through that one, now A, B or C, let's say A goes next, it can go through any one except the one that D went through. So it's got a 4 in 5 chance. But then the next mouse wants to go through the same one as the last one, so 1 in 5, and then the last mouse, 1 in 5. And we get a probability of 4 out of 125. Okay. So then they said, well, hang on. What's the probability that any 3 of the 4 mice go out the same exit, but then the other mouse uses a different one? Right? So how's that different to what we just did? Well, we just said A, B and C go out the same exit and D goes out a different one. This next question is saying any 3 go through the same one. So we just worked out probability that D uses a different exit is 4 in 125. So therefore, logically, probability that A uses a different exit would also be 4 in 125. Probability that B uses a different exit would be 4 in 125. Probability that C uses a different exit, 4 in 125. So therefore, probability that any mouse uses a different exit to the other 3 would be 4 lots of 4 125s, 16 in 125. The final part, I think this was the final part of the question. What's the probability that no more than 2 mice go out the same exit? Okay. Well, this is how I worked it out. Using the complementary event idea, you might remember. Remember, all probabilities add up to 1. So sometimes, rather than finding the probability of what I want, it's easier to find out the probability of what I don't want and subtract it from 1. And that's the idea I'm using here, because we've already worked out these other 2. Remember, we worked out the probability they all go through the same exit. And we've now worked out the probability that 3 use the same exit. Look at what we want to find. No more than 2 use the same exit. In other words, 1 uses the same exit, that's a bit silly. 2 uses the same exit, but we can't have 3, so I want to subtract that, and I can't have 4. Well, they're the 2 things I've already worked out, so let's not waste time, we'll just subtract what we've already worked out. So that complementary idea comes in very useful in probability questions. So we get 108 in 125. Alright, so that's the basic counting idea. But that then leads us to this idea called permutations. Now, what's a permutation? A permutation is simply an ordered set of objects. So we get the objects and we arrange them in a specific way. That's what we call a permutation. So we're going to look at a few cases. We've got a set of n different objects and we're going to arrange them all. So that's what we're saying here. We're an ordered set of n objects from a set of n. Going to use them all. Okay, so if we arrange n objects, and let's say we're just lining them up out the front here, the number of ways we could do it. Well, imagine, there they are, the n objects are in the corner over there, and I'm going to get them to line up. So I go over here, and I say, look, someone's got to go first. Who wants to go first? How many different ways could I get an object to go first? Yeah, n. So now I'll go get the second object. Okay, well look, that one's already gone. Someone else would have come along. So the next one would be n minus 1. And then it would be n minus 2. And so on and so on. But we're using all the objects. So at some point, I must get to the situation where there's only 1 left. Come on, join the others. And so we get down to the last one's 1. So n times n minus 1 times n minus 2, all the way down to 1. You may recall in maths we have a much neater way of writing that being factorial. N factorial. So if you want to arrange all the objects, it's that many factorial. Right. So let's put some actual numbers in there. 5 boys, 4 girls, going to arrange them in the line. How many ways can I do it? No restrictions. Well, if there's no restrictions, the fact that I've got 5 boys and 4 girls is irrelevant. It's just 9 people. I want to arrange 9 objects, so it's 9 factorial. Simple as that. What does that work out to be? There you go, 362,880. Mind you, it's much more fun if we put restrictions on it. So let's say, no, let's have the boys and girls alternating. How many ways can we do that? Now, we've got 5 boys and 4 girls. What's the first decision I must make? Well, boy has to start, if you think about it. Otherwise, you're going to run out. If you started with a girl, you'd run out. Now, if there was the same number of boys and girls, then okay, the first decision would simply be, will I pick a boy or a girl first? But in this case, there is no choice. So we always look after any restrictions first when we're working it out. So in this case, we don't have that restriction of, do I pick a boy or a girl? So the first one must be a boy. So I'm simply going to say, well, there's one way we can start this. That's with a boy. Okay? As opposed to if I could choose, I'd say, oh, there's 2 ways. I could start with a boy or I start with a girl. But in this case, got to start with a boy. All right, now I'm going to arrange them. Okay, fellas, you just want to line up over there? Thanks for that. How many ways can we arrange them? 5 factorial. Brilliant. Okay, girls. Now you go line yourself up. But when you sorted out your order, just slot in between. So it's just 4 factorial. So they're just going to slot in between all the boys, so they alternate. So I don't have to worry about, oh, I'm going to pick a boy, then I'm going to pick a girl, then I'm going to pick a boy, then I'm going to pick a girl. It's just the same as saying, okay, I'll arrange the boys and I'll arrange the girls. So 2,880. Which then, again, leads to the whole point of this. What's the probability of the boys and girls alternating? Well, it'll be 2,880 out of 362,880. 1 in 126 ways of that happening. But hang on. Forget about them alternating. Everyone's over here. We've got 2 girls who are great mates, and they're saying, we're going to be together. All right? So you look after the restriction first. And you say, okay, you 2 are going to be together. Can you work out how you want to arrange yourselves? So how many ways can those 2 arrange themselves? 2 factorial or 2. So we look after that first. Okay, they've arranged themselves. Now, as far as I'm concerned, those 2 are 1. They've decided the order they're going in. They've got to move together in that order. They can't change. So instead of now arranging 9, I'm arranging 8 objects. So 8 factorial. So the 2 girls who are now in a group of 1, got to stay together, and 7 others. So 8 factorial, giving us 80,640. All right. So that's when we use them all. But what happens if we don't use them all? So I've got k different objects, but I'm going to pick from n, and k is less than n, obviously, because I'm not going to use them all. How does that change? So let's do it again. We've got n different objects in a line, but I'm only going to arrange k of them. How could I do it? So I go over here in the corner, and we want to start again. Someone go over there, will you? There's still n ways of getting that first object. There's still n minus 1 ways of getting the next object. There's still n minus 2 ways of getting the third object. But I'm not going to go all the way. I'm going to stop at the kth object. How many ways of arranging the kth object? Have a look. The pattern is there in front of you. What would it be? For 1 object it was n. 2 objects it was n minus 1. 3 objects n minus 2. K objects n minus plus 1. Okay, so that kth object we're going to put in there. Now, of course, to go and work that out takes a long time. So I think about it a little bit differently. Okay, hang on, no. That's not what I'm going to work out. I'm going to work that out instead. That's much easier. Because if you look at it, all I've done is multiplied by 1. The numerator is the same as the denominator, but have a look. the top now becomes n factorial. The bottom is n minus k factorial. A lot quicker to work out. Essentially what we're doing is we're dividing by the number of ways the objects that I didn't choose could be arranged. I didn't end up using them. So I'm dividing all of those possibilities out. That's essentially what we're doing. So we get n factorial on n minus k factorial. On most modern calculators, you've got a button that'll do that for you. And NPK, sometimes found on the multiplication or division? Division? Multiplication. On the multiplication key, you'll find it. Okay. Still important you know that formula though, because sometimes you might have a question that doesn't use an actual number, and you might have to do algebra. So n factorial, n minus k factorial. Let's do some examples. So we have the word problems, appropriate because we're looking at some examples. We're only going to make 5-letter words, so I'm not going to use all of the all the letters. How many are possible if there are no restrictions? Well, if there's no restrictions, it's 8p5. I've got 8 letters that I can choose from, and I'm going to use 5 of them. I'm only going to arrange 5 of them. So 8p5, 6,720. For those of you that have an older calculator without the permutation button, that would be 8 factorial on 3 factorial. Those of you who've got an even older calculator that doesn't have a factorial button, that would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. Oh, what do you know? The 5 times 4 times 3 times 2 times 1 cancels, leaving me with 8 times 7 times 6. Voila. Yes, that's how I used to have to do it back in the old days. Okay. Let's put a restriction on it. The word has to begin with P. Has to begin with P. Always look after the restriction first. How many ways can we start with a P? One way. We'll start with P. It's the only way. Now what is the question? I need another 4 letters. So it's like saying, hang on, how many 4-letter words can I make from problems? So 7p4. So 1 times 7p4, 840 words now. Alright? What about P's included? Doesn't necessarily have to be at the start. In fact, no, it's not going to be at the start. We're going to put it in, not at the start. And by the way, we don't like the letter M, so we're not going to use M. How many ways? Again, let's look after the restriction. So P is included, but not at the beginning. So 4 ways I could do that. Right, there's 5 spots to put the letter. Can't put it at the beginning. Okay, I've got 4 spots. Now, M is excluded. I need another 4 letters. But it's only 6p4 now, because it's like saying, how many 4-letter words from Robbles? I've used the P, M I'm not allowed to use, so 4 from Robbles. And the answer, there it is, 1,440. Now, 6 people are in a boat. The boat's got 8 seats. 4, and by the way, that's not how we spell 4 in Australia either. That is misspelt. Okay. So what's the probability that Bill and Ted, they want to go on the left side, and Greg, he wants to go on the right-hand side? So it's a probability question. First thing I always do is work out number of ways, no restrictions, because that's going to go on the bottom of my fraction. So in this case, well, there's 8 seats. I'm going to end up using 6 of them. So 8p6, 20,160. That'll go on the bottom of the fraction. Now let's work out our restrictions. Bill and Ted are being awkward. We have to be on the left-hand side. Okay, well that would be 4p2. There's only 4 seats on the left-hand side. Going to use 2 of them. And so Greg comes along and says, hey, if they're going to be on the left, I'm going to be on the right. Don't want to be the same. No way. So that would be 4p1. And then, of course, the other people, how many have we got left? 3 people are just looking at them going, what does it matter? We'll go anywhere. And so now they can go in the 5 remaining seats. There's 3 that they can choose from. And we end up with, when we put that all together, 2,880. So our probability becomes 2,880 over 20,160, which simplifies down to be 1 in 7. 1 in 7. Last example. I think this is the last example. Bit more recent. 2006 paper this one came from. Still a fair while ago now. What's that? That's even that's 12 years ago. Sophia has got 5 coloured blocks. One's red, one's blue, one's green, one's yellow, and one's white. Although there is some debate about whether white actually is a colour. Exactly. But for the sake of our question, white is a colour. Right. So she stacks 2, 3, 4 or 5 blocks to make a tower. In other words, one block by itself is not a tower. It's what we call a block. Very good. So, the question is, how many different towers are there that are 3 blocks high? Okay, 5 blocks to use. I'm going to arrange 3 of them. We get 60 different towers. Second part of the question. Well, how many towers can she make all up? All right. Well, 2 block towers, that'd be 5p2. That's 20. 3 block towers we just worked out. That's 60. 4 block towers, 5p4, 120. 5 block towers, 5p5, also 120. So in total, 320 different towers we could make. All right, that was a heck of a lot of theory to start off with. 10e